one would probably expect, since currents consist of moving charges, that one would expect that there would be a magnetic force on a current carrying wire from much the same mechanism that we had the force on a point charge. And so let's look at that. I want to consider a constant current I and going in a straight wire, so fairly specialized case of total length L, and it's in a uniform magnetic field B. So B is constant everywhere. And the way I've drawn it, the total length of this straight line segment is L. It has a cross sectional area A. Magnetic field is up everywhere, and the current is going in this direction. And we know that currents can be thought of as positive charges going in this direction, and I know that there's a force on positive charges. So um, now I could look at one of those positive charges, and the force on just that one charge would be the Q. I call them Q sub F. Probably just Q is fine too. But these are the charges that are free to move, uh, and the velocity crossed into the magnetic field. And the velocity with which they move is, of course, the drift velocity. Now we know really that producing current this direction is negative charges going the other direction, drifting the other with a drift velocity. So this velocity is just the drift velocity. And again, a lot of people leave that as just V. But I'll go ahead and write it as V sub d for drift velocity. I've got my charges that are free to move. And now if I want the total force, well, there's all kinds of positive charges moving in this direction, drifting in this direction, making this current go in that direction. So I'll assume in this segment I've got a total of n, where n's a very large number, roughly one per atom. So it's going to be something like 10 to the 23rd is the number of particles. Uh, so this n is huge. Uh, I can relate that to the number density of charges that are free to move. Remember, that's just the number of charges free to move divided by the volume they're in. And in our case, the volume is just this wire. It's the total number of particles divided by the cross-sectional area. Well, the volume is the area times the length of this little thin cylinder here. I've got this picture. If I view it from this end, and that's the side picture here, I can get the direction of the force, which is really indicated over here, but it's a little easier to see from this perspective. I is going into the page, the charges are moving in that direction, and they all have they're all going the same direction, and B is up, and so the V cross B is going to be in this direction, and I've got that indicated over here as well. Now it's just a matter of rearranging all of this. So I know N from this expression, N sub F is NAL, so I can get N as the number density of charges free to move times A times L. And I substitute that for N up here, and I have this expression. And then I just have to remember we had a relationship between the current density J vector and the drift velocity, and it was simply Q times N sub F. And if you note, I've got an N sub F here, I've got a Q, and I've got the drift velocity. So these are the charges free to move. So I can replace N, Q sub F, V sub D with J, and I'm left with still this AL, I across B. And the current density, the direction I could call it, it's a magnitude J, let's call it, in the J hat. But J hat is current and current density always have the same direction. So the current density is a vector that points in the direction that the current is going. So it's going in this end of the page when I look from the side view over here, or from the end view. So I'll write it like this, and I can group L with the J hat, and I can group the A with the J. But I know that J is just the current per cross-sectional area. And so when I make that substitution, the two A's go out, and I've got L and the J hat. That's the direction the current's going crossed into B. And then I've got a nice little expression. Provided I define this L vector as being the length of the straight line segment in this direction of J hat, which is also the direction as the current flow. So altogether then I get the force on this current carrying wire is I. L vector, if I define it up in that fashion, L vector is in the same direction, but is just the length of the straight line segment, and then the same direction as current's going. In this case, L vector is going in, B vector is going up, and when I take that cross product, it gives the same direction as before, except now I've got a different expression. The thing that's nice about that expression is all of this, I, L, B, those are all things that can be measured easily. I measure the current in this straight line wire segment. I can measure its length, and I know this, and I can measure or apply a known magnetic field and get the force on it. So this is really a macroscopic thing, and in reality, this was the force that was first formed. The magnetic force was first discovered, and the there's a few issues that you may well know. Is that most wires will eventually they get bent around in different shapes. So here's a wire that's curved. So we need and also the magnetic field could vary everywhere along this. But I can take an infinitesimal, just a small segment of the wire, I call that DL vector, and so DF due to a infinitesimal length DL vector. So it's not all the length of this from A to B. It's just part of it. And but the current's the same everywhere. And the magnetic field, well, I'd have to take the magnetic field that exists at this point in DL, and that way we could also have a situation where the magnetic field varies all along here. And then to get the total force on this complete wire segment, I just have to add up all the DFs on all these little infinitesimal DLs all the way from the end. Have to add them up as vectors, but ultimately it becomes a continuous sum of all of this stuff from A to B. And I generally think about this as this integral is adding up. It's an integral over dl, but it's over all of the stuff that lies to the right of it. So it's acting in that fashion. Well, what I've called dl vector, and I think your book uses maybe capital L vector as well. I usually use d script L vector, and some books will use d small s. And if you remember, dr vector is dx in the I hat plus dy and j hat plus dz in the k hat. And the arc length, which would be here, arc length vector, is the magnitude of this, is the square root of dx squared plus dy squared plus dz squared. So you may have seen this dl vector or d script L vector in other books, certainly. Or you may have seen it as arc length vector, where this is, using the distance formula, is the arc length along the curve. The way I think of the dl vector, d little l vector or dl vector, it's a vector that infinitesimal, but it points along the wire in the same direction that current is flowing from A to B, but it's an infinitesimal unit. Well, there's another way to get that same formula. Sometimes people like this, although there's advantages to both. Another way to look at it is this: I know the force on a charge is Q V cross B, and let's suppose I don't have a big charge here. I've just got a very, very small, which is dq. then it's going to produce a very small force. And so the force dF produced by a amount of charge dq moving in this current is dq v cross b, where v is the velocity it's moving and b is the external magnetic field. And velocity, I could write that as dr vector dt, but to me, dl vector is a dr vector along the wire. In this case, x, it's dx, but it's in the direction that the current's going through it. And I can, so velocity is the displacement, dl vector, in this case along the wire dt, and that will give me the velocity down the wire. And I can move this dt underneath q, so just move it underneath the dq, and that just becomes the I. And again, I get df is equal to I dl vector cross b for this the force on an infinitesimal segment of the wire that's carrying a current I in an external field. Notice if I and b are fixed, then I can integrate this to get the total force, and it really just is the integral of dl vector, which turns into capital L vector for the total wire if it's a straight line segment.